Okay, so in case you have any doubts, you can stop me anytime. Okay, so since no one is asking any questions, I'll proceed with my discussion. So last class we were discussing about cooling and dehumidification process, where let's say this is the entry of the air into your evaporator coil. This is the entry condition. And if this is the process line, the air follows. So this is the exit condition. Okay, so this is one, this is two. If you extend this line all the way till the RH equals to 100% line, whatever temperature this denotes, that is called the apparatus dew point. Okay, and we define something called as bypass factor. So bypass factor is nothing but T2 minus TADP upon T1 minus TAD, which is equal to 1 minus, if you remember how we define the effectiveness of the heat exchange process, 1 minus epsilon. So what is the physical significance of this ADP? It denotes the dew point temperature for that particular apparatus at which you can bring the air to complete saturation. So if you were to cool the air from this inlet condition till this point, you will bring it to saturation condition. So this is cooling plus dehumidification. It is not just cooling. So this is not the dew point temperature that we have discussed for the incoming air. In attaining the dew point temperature, we just sensibly cool. Here you are sensibly cooling as well as you are dehumidifying. So if you are doing both the process and if you attain this temperature TADP, at that condition, your air coming out from the coil would be saturated. Okay, and this is effectively telling you what should be the coil temperature, because the process that your air follows as it passes through the coil is the line joining your inlet condition to the ADP. So this also tells you what coil temperature you will have to maintain. Now, where it lies on this line will be dependent on the effectiveness of the heat and mass transfer process. So there are two parameters which decides the outlet condition from this evaporator coil. Okay, and now in case you want to control the outlet condition, so you have two parameters. One is setting the coil temperature, the other one is setting the effectiveness of the heat and mass transfer process. So that's why in your residential ACs, you have various modes. So those various modes are effectively controlling the coil temperature and the effectiveness of the heat transfer process. Okay, so whenever I'm telling heat transfer, it's heat and mass transfer because you also have dehumidification. And we also looked at what are the factors which affect the effectiveness or bypass factor, whichever way you want to call it. So one is, so these two parameters are basically the heat exchanger design. So number of rows of the evaporator coil. So how many rows you have provided, what is the fin pitch. So if you have closely spaced fins, so you will have more number of fins in your heat exchanger. So this increases your area. Increasing the number of rows of the evaporator also increases your area. So if you have large heat transfer area, so heat and mass transfer area, then that is going to increase your effectiveness. Okay, you are going to go very close to your coil Yeah, sorry for the interruption. There was some internet issue at my office. I hope I am audible and the slide is shared.
Yes.
Yeah. So what I was discussing is if you look at the cyclometric process that happens inside your evaporator, so your TADP, that is your apparatus dew point, that is effectively the coil temperature you need to maintain to follow this process line. And where exactly the exit will lie on this process line is determined by the effectiveness of the heat and mass transfer process. And the refrigeration industry, instead of using effectiveness, they use the factor called the bypass factor. So, so in principle, what your air conditioning device can control is both your coil temperature as well as your effectiveness. Now, in order to understand what effectiveness depends on, uh, you can actually carry out experiments with various heat exchangers, okay, and then identify that how your bypass factor or your effectiveness of the heat exchanger changes. So if you increase the number of rows of the evaporator coil, or if you increase the number of fins, the effectiveness of the heat exchanger increases, which is quite obvious. Like if you increase the area, you are expected to have a much more residence time for your incoming air. So if you have only 4 rows, or if you have 5 rows, so if air is coming in, so this is the top view, hits the first row, cools down, second row further cools down, third row further cools down, fourth row further cool down. So if you increase the number of rows across which the air is blown, definitely you are going to attain a temperature at the exit, that is T2, much closer to the coil temperature. And if you reduce the number of rows, you will have exit temperature significantly higher than the coil temperature. By coil temperature, I mean what is the refrigerant temperature inside the coils. Okay, or similarly, if you increase the number of fins, you are going to increase the area, thermal area, which comes in contact between the heat exchanger and the incoming air, and you are going to have similar effect. So whereas if you decrease the air speed, then also you increase the effectiveness of the heat transfer process because you have lesser mass flow rate of air. So if you remember, we have been discussing about the external regime. Then the external regime, the slope, the temperature change on the external regime side, that is air in this case, it will be higher. Okay, assuming for the same amount of heat transfer, you will have this slope significantly higher when you have lower air speeds compared to when you have very high air speeds, you will have lesser amount of temperature difference between T1 to T2. So that will also affect the effectiveness of the heat and mass transfer process inside your coil. So these are some experimental results which are shown. Of course, once you have designed your heat exchanger, you cannot change the number of rows and number of fins. So what you can control in an actual air conditioning system is the airspeed. Okay, so the airspeed here it is written as phase velocity. This name is given because the airspeed. Now, where to measure the airspeed? Should I measure it in between the coils, or should I measure it outside the coils? So what this phase velocity signifies is whatever the airspeed is, uh, it has to be averaged over the entire area across which it is flowing. If you again remember the experiment we have conducted, in one of the experiment, I was measuring the airspeed for the condenser side. So I had measured it at various locations. Okay, I could not put my sensor inside the in the gap of the fins. So I cannot measure the airspeed over there. So you have fins also here. So I cannot measure the airspeed here. So all I can measure it is outside this heat exchanger at certain locations, and then I'll average it out. So that is called as the face velocity. So face of the heat exchanger. So various speeds are given over here and various number of rows are also given. So this experiment was conducted for a particular fin pitch. So fin pitch is fixed. So number of rows will definitely increase the number and the area available. So if you see, if you uh, look at the number of rows, if you increase, you have your bypass factor reducing. So number of rows increasing, your bypass factor is reducing. Okay, whereas if you increase the airspeed, your bypass factor is increasing. So if basically your effectiveness over here is 0.48, the effectiveness over here is 0.44, effectiveness over here is 0.41. Okay. Whereas if you look at the effectiveness at this condition, where you have 6 rows, you have almost like 0.978 as the effectiveness. Okay, so if you have 6 rows, you have very good effectiveness. But normally what we then again optimize. So if you increase the number of rows, definitely you are going to have better effectiveness. So we try to optimize in terms of fan power. So if you have to blow the air across 6 rows, so there are 2 rows in this example. So you will have 4 more rows. So you have 6 rows across which the fan has to now blow the air. So it has to do more work. Okay, so we optimize in terms of the fan power required and the effectiveness that we can obtain. Normally, you will see most of the manufacturers will not go beyond 70% effectiveness. As it is, in order to obtain 70% effectiveness, you will require 2 to 3 rows. This is the typical number of rows that you will have in your indoor unit. Okay, your indoor unit will have 2 rows of evaporator coil. So air will come in, pass through one row, the next row, and then it goes out. Okay, so this is how uh, the the 2 evaporator rows are placed in this manner. So it's in form of a triangular shape if you look at from the side. So most of the heat exchangers, you will see they consist only of 2 or maximum 3 rows you may find. So going to 6 rows is not practically desirable from the fan power point of view. Any questions? So this figure just tells you what is the logic behind the industry defining a term called bypass factor. What they understand by bypass factor is if you have 1 kg per second of air flowing into your evaporator, X fraction of it is completely bypassed and 1 minus X comes in complete contact with the evaporator. By complete contact, I mean this T1 will go to TADP and the X fraction, the fraction X, it remains at T1. Okay, so now T1 and TADP mixes back to obtain the outlet temperature that you actually have, T2. So this is just an equivalent model of obtaining this T2. So what is that X fraction which if completely bypasses the coil and 1 minus X passes through the coil with full effect, full 100% effectiveness. And you get back the same temperature once you mix this bypassed air and the air which is of destruction. So, am I audible?
Yes, sir.
Audible. Institute. Slide is visible.
Yes, sir.
I was talking about the energy equivalence of this bypass factor. Has coined this bypass factor term because what they see the T2 as the outlet, what they have broken down into components. One component which comes in complete contact with the evaporator coil. By complete contact, I mean temperature exiting the evaporator coil is the rest of the amount, which is actually the bypass amount, that remains as T1 and they mix form T2. So this is what industry means by bypass factor, whereas in academia we are more uh, uh, what you can say more introduced with the terminologies as effectiveness and efficiencies, and so it's slightly different, but they are just a complementary term. Then I think I have already discussed briefly in the last classes. Many a times you may not want to follow this particular line. Okay, so if you provide a coil temperature ATP here, you will be following this particular line. But your desired process line could be this blue line. Then how do you attain this is you have to break down your entire process into multiple cooling and humidification and heating process. So at every given inlet condition, if you draw a tangent to the RH equals to 100% line, that gives you the limiting coil temperature and the limiting process line, which you can attain by using one single cooling and dehumidification coil. If your process lies within this zone or maybe somewhere above this, you are safe. But if your process lies below this line, okay, then you will not be able to attain the desired process using one single CND process. So one single cooling coil will not provide you this blue line. So then you have to go into multiple processes. So one way is you go up till this point and then peak. But then you will see with this ADP going up to this point may not be practically possible because you will require a lot of effectiveness. So either you provide huge number of rows so that you get very high effectiveness, or in case you can work with lower velocities of air, extremely low velocities of air, then also it might be possible. But in most scenarios, you will see that getting such high effectiveness is practically not possible. So you will probably get up to here, then you will heat it, heat the air, sensibly heat, pass it through a heating coil. That heating coil is called the reheater coil. After cooling coil, you reheat, and then again you pass it through this coil. So this would be the next process line. Maybe you attain up to here and then reheat. So how many processes you will require depends on first what is the slope of this blue line, second what is the limiting CSHF line, so this is the limiting coil sensible heat factor line. Okay, so this is the limiting process line that you can have in your single cooling and humidification coil. So these two will determine how many processes you will require to attain your final condition. Let's say your blue line, instead of this, it was probably somewhere here. then you could have attained the same process by one cooling coil and one reheating coil, this and this. But now you require an outlet condition over here, okay, then it becomes quite difficult to attain the same humidity ratio using one single coil. So you break it down into two processes and then reheat. Cool, reheat, cool, reheat. So definitely this blue line is not possible in your residential ACs. Domestic AC, domestic air conditioners cannot provide you this blue line because they just have one cooling coil, so it can provide you this kind of a process. Okay, now you can see that if you have or if you are living in an environment where the humidity ratios are not very high. Okay, let's say this is the temperature and your humidity ratios are somewhere here. Let's say you are living in Delhi or somewhere in the northern part of India. So then you can see that if you draw a tangent, this is the amount of dehumidification that you can obtain. Okay, and this is the amount of cooling you can obtain, sensible cooling. Whereas you can have, I draw it again, you can have this as the exit humidity ratio from your coil. Whereas if you are living in a place where you have very high humidity ratio, let's say here, then if you draw the tangent, you may see that now you can only obtain an exit air temperature theoretically, that is the minimum possible is this, and the minimum possible humidity ratio is also this. Okay, so since you have only one cooling coil, you get limited by this limiting CSHF line. Whereas in your central ACs, where we can have multiple cooling coils, multiple heating coils, over there you have much more flexibility. Any questions? So examples, I will not be solving them as such. I'll just show you if you are using EES how to write the code. But you will see that it is much faster to use the charts over here than even writing the EES code. So let's look at this example so that I can tell you how to write the EES code in case of psychrometric processes. Using the charts, it is straightforward, just marking the state points and reading all the enthalpy values and temperature values. So in a cooling coil, you have air flow rate of 2.4 kg per second. The atmospheric pressure is given, temperature and relative humidity is also given. So this is the inlet condition of air, which is cooled and dehumidified to a temperature of 15 degrees C and 80% RH using chilled water, which enters the coil at 7 degrees C. If the temperature of water at exit of the cooling coil is 12 degrees C, find the conditions. So what we have to find is what is the required flow rate of chilled water, what is the cooling capacity of coil in tonnage, what is the sensible heat factor for this process, what is the coil bypass factor and coil ADP. So quickly see how to write the properties in ES. If you want to call enthalpy, first of all, let's get H2O. So whenever you write this fluid name air H2O, ES understands that it has to now look for properties which are for moist air. If you just write air, it will be dry air. Air H2O is the fluid name which we have to write for all psychrometric processes. And if you want to say call for enthalpy, so $, is just a variable name for your fluid name. Instead of writing air H2O every time, you can write $, or if you prefer, you can use air H2O. Pressure you will have to give. So now in case of ES, you always have to give all the three properties. While drawing the chart, we have assumed that the atmospheric pressure is constant, but the ES code is written for variable atmospheric pressure also. So it includes all the information at lower and higher pressures. So you have to tell exactly what is the and then the dry bulb temperature is relative humidity fraction. See what it gives. It will give you the enthalpy. Now, what are the other functions you may require? Let's say you want to know what is the humidity ratio. And in fact, you can, since every time you'll have to write. So again, you will have to give two other properties. So let's say I know the so then it will give you the value of omega, that is mass of water vapor per unit mass of dry air, and the units are kg per kg. Your charts may contain units as gram per kg. So this is effectively 9.8 grams per kg of dry air. Okay, or you can also give the R value. Require two other properties. And the function for calling relative humidity is L-hum. So you get back 0.5. So these three are the functions which you will use quite frequently in case you prefer to use ES. Enthalpy, HumRAC, which is nothing but humidity ratio, and REL-hum, that is relative humidity. So now let's come back to this problem. So how do we solve this problem? What is the required chilled water flow rate? So first always draw the schematic of whatever is given. You have a cooling coil through which air passes. Air inlet condition is 25 degrees C, 50% RH, and mass flow rate is 2.4 kg per second. Nothing is given. Assume this to be as the dry air flow rate. That is the default condition that we use. And it is dehumidified and cooled to 15 degrees C and 80% RH. So chilled water passes through this coil. Water enters at 7 degrees C and it leaves at 12 degrees C. Okay. Mass flow rate of water is what has to be determined. So what do? Call this state 1, state 2. Let's call this as water state 1, water state 2. So what do? Apply energy balance, as simple as that. So m dot air times, so whatever is the enthalpy change on the air side, that has to be balanced by the water side. P of water 1. You will get the requisite value. So this is nothing but Cp delta T for water, and this you can obtain from the ES or from the charts, because you know the state 1 and state 2. You also know the mass flow rate of it. Any doubts? Calculate the cooling capacity of the coil in tonnage. So we use the conversion factor of 3.516 kilowatt being equal to the 1 ton of cooling capacity. Then we have to obtain the sensible heat factor. So how to obtain the sensible heat factor is, we know the inlet condition as 25 degrees C, and we know the exit temperature as 15 degrees C. So in your psychrometry chart, you can mark these two points. Okay. And then finish off the triangle. This is your latent component, this is your sensible component. This is 15 degrees C, 25 degrees C, and whatever relative humidity lines pass through this. So just determine this value, and you already know what is the total enthalpy change across the moist air. So this divided by the total. Now in case you want to write ES function, then how do you do that? How do you obtain the fraction of sensible component for the process? 1 to 2 using ES. So what is constant over here in the sensible process is the omega. So make use of this fact. So obtain the omega at this condition, omega 2. Okay, and you have to get the intersection of these two. What would be this temperature? 25. What would be this temperature? 15. Okay. What would be the omega over here? Same as omega 2. So you call for enthalpy at 25 degrees C and omega equals to omega 2. And pressure is always whatever is given, atmospheric pressure. And call for enthalpy at omega equals to omega 2 and temperature equals to 15 degrees. Okay. Take the difference, that will give you the sensible component of the enthalpy change. And you already know from the part A what is the total enthalpy change across the cooling coil on the air side. Just take the reference. Is this clear, or do you have any doubt? Coil bypass factor and coil ADP. This is quite simple using your psychrometry chart. Now think of a way how to obtain the same thing in ES. This you think how to obtain through ES. Okay, this is your homework. From the chart, it is straightforward, and you take the understanding from the chart and how to write an ES code for obtaining the coil ADP. Think of a way of obtaining this using a simple thing. It will be 2 or 3 lines of code in ES. So these answers are given, so you can just tally once you solve the same problems at home. What is interesting is to see the coil bypass factor. Bypass factor is 0.3, so it is 70% effective, and the coil ADP is 10.7, so somewhere in between 7 and 12. Okay, because we are using chilled water, both the internal regime, that is the fluid which is cooling, as well as the external regime, the fluid which is getting cooled, both are undergoing sensible heat transfer. Yeah, of course, on the air side, you also have some latent heat transfer. So both will undergo a temperature change. So external regime is changing its temperature from 25 to 15, whereas the internal regime is going from 7 to 12. So in this case, having one coil temperature is going to be very difficult to determine. But you still get a coil temperature, that is some apparent coil temperature you will get by extending the process line on your psychrometry chart. So this is like an evaporator coil temperature that you require to maintain. But what you have on the coil side is not refrigerant boiling. You have cold water coming in at 7 and leaving at 12. So this will give you some average idea what should be the coil temperature. Next process which we are going to look at is cooling and humidification process, which we had partially looked at when we were discussing WBT. So in WBT, how we attained the wet bulb temperature was we had incoming air at certain temperature and humidity ratio. It passes through a wicking material. Okay, that material is always kept wet. So that's why we have a wicking material, or instead of having a wicking material, you can have a pad which is always kept wet by by use of a pump. You pump water and allow it to uh, wet the entire pad. And then as air comes in contact with this pad, it will humidify, and the heat of the latent heat of vaporization would be provided by the incoming air itself. And that will only happen if you have this entire box completely insulated. There is no heat transfer from the outside. So the only way that liquid water can evaporate and become a part of the flowing air is if the incoming air itself cools down and provides the requisite latent heat of vaporization. So then what you have is cooling and humidification. So air leaving this box will be cooled because it has supplied the latent heat of vaporization, but it will be humidified because it has picked up moisture. Okay, and the practical device which tries to attain. So if you have R equals to 1 at the exit, is 100%. Then the temperature corresponding to the incoming condition is called, so whatever exit temperature you get is called the WBT. And the practical device which tries to follow this process line is a desert cooler. Okay, but in a desert cooler, there are certain things which will not adhere to the assumptions that we have made. First of all, this adiabatic chamber. Okay, your desert coolers are not perfectly insulated. So you can have some heat transfer from the ambient to the air which is present inside the box. And second is you will attain 100% at the exit if you have extremely large heat and mass transfer area. Very similar to what we were discussing in cooling and dehumidification. So this pad has to be extremely large. Air speeds have to be very low. So again, you have to do something to increase the effectiveness. Okay, so if you have infinitesimally small flow rate and infinitely large area, you would come to this saturated condition. But of course, then your cooling capacities and all those parameters which we require from a desert cooler, we require some cooling capacity. For that cooling capacity, we require some finite airspeed. Okay, and we cannot have an infinitely long evaporation pad. So hence your desert cooler will never attain the WBT because of these two issues. Okay, effectiveness will be less than 1 and your box is not completely insulated. So the theoretical process line on your psychrometry chart is your WBT line, which is already marked on your psychrometry chart. It may look very similar to the isenthalpic line, but it is not exactly that because you supply some liquid water into your desert cooler or into your saturation chamber. So the incoming enthalpy of this liquid water also needs to be included. If you neglect that, then it becomes an isenthalpic process. So H1 equals to H2. If you neglect the enthalpy of the liquid water that you always stock up in your desert cooler, then it becomes H1 equals to H2. Okay, so this is your WBT process line. Your desert cooler at least tries to follow this line, but it will not reach this saturation. It will probably stop somewhere here, and because of some heat transfer from ambient to the box in which your process is happening, you may gain some heat, and instead of attaining this, you may attain a condition over here. So you can break down the process somewhat like this. So you will have this as your exit condition. You should have lied on your exit conditions should have lied on the WBT line, but it may not lie because of the heat transfer from the ambient. Okay. Now, if I neglect that heat transfer, then you will attain somewhere here. And what determines where you will lie on this WBT process line is the effectiveness of the heat and mass transfer process through this pad. So air is drawn in through the sides of this cooler. So you can give multiple layers of this pad. You can have very large area provided, but then you will require more blowing power. You may think that I will attain better effectiveness by reducing the airspeed. That is also possible, but then again you will require a very large desert cooler for you to provide the same cooling capacity. Okay, so the exiting temperature here could be somewhere between your T in and TWB. So over here also the effectiveness of the desert cooler can be defined as T1 minus T2, T2 being the actual temperature of air leaving this desert cooler, and T1 minus TWBT. So this is the theoretical maximum temperature difference that you can have between T1 and T2. Okay, theoretically T2 should be TWBT. This is a simple sample problem. So in an evaporative cooler, you have 0.3 kg per second of air, which flows, and the incoming condition is 42 degree and 18 degree WBT. Quite dry air. If you have large difference between DBT and WBT, it means it's quite dry. If you plot the state point on your psychrometry chart, so you have to mark 42 degree line. This is your DBT, and then over here your WBTs will also. Let's mark the incoming point. So 42 degree Draw a line and 18-degree WBT. So your WBTs are marked over here, 10, 15, 20 like this. So this is the dotted line for WBT, 15, 16, 17, 18, 19, 20. This is your 18-degree line. Follow this constant WBT line wherever it intersects the 42-degree line, somewhere here. A very dry air. So this is your incoming air state. And then what is given in the problem is effectiveness of the evaporative cooler is 80%. So 80% means you should have attained 18 degree as the outlet temperature from your desert cooler. Okay, so the maximum temperature difference is 24, and this desert cooler is giving you only 80% of that. So just check what is that value, and it will come now to be 19.2 degree. Subtract from 42. So that is your exit temperature. Okay, so that is your exit temperature, 23 degrees. So let's mark the process on this chart. 42, and this was the line somewhere here, and you should follow this line, but you are only attaining 80%, so you will be able to get 23 degrees. 23. So instead of attaining 18, you are only attaining 23. So this is your process line. So this is WBT, this is your DBT, this is the incoming state 1, this is the exiting state 2. Now it is asked what is the required makeup water in kg per hour. So once you have identified the process line, so this is 1, this is 2, just check the humidity ratios, W2, W1. So M of air times W2 minus W1 will give you the amount of water which has evaporated. So mass of water which has evaporated per kg, per second. Convert it into per hour. Okay. So I know the W2 at the exit of the desert cooler. I know W1 at the inlet of the desert cooler. The difference is whatever the amount of water would have evaporated. That is the makeup water I have to supply. Next part is what is the sensible cooling capacity of this evaporative cooler if it is used to maintain a room temperature at 27 degrees C. So this 23-degree air goes into a room to maintain 27 degrees. The room temperature is maintained constant at 27 degrees. So air comes from the desert cooler at 23 degrees C. Okay. Picks up all the heat inside the room, and definitely it also has to exit. Okay, it's not as if the desert cooler is pressurizing the room. So that's why when we have a desert cooler operating in a room, we always tend to keep a window or a door opposite to that desert cooler, if not completely open but partially open. Otherwise, your room will become very humid after some time. If you continue to supply humid air into the room with no exit at all, then you will start to feel uncomfortable. So whatever air is being blown into this room by the desert cooler has to be taken out also. But the air exiting this room will have a temperature of 27 degrees. So it is asked what is the sensible cooling capacity of this evaporative cooler. It is nothing but M air, whatever the air flow rate is, 0.3 kg per second, into Cp of dry air into the delta T, 23 degree rising to 27 delta T, that is 4 degree. So that is the sensible cooling capacity provided by this desert cooler. Please stop me anytime when you find something is difficult to follow or you didn't understand any question or any part of the question. Next process which we come across, well, may not very common in our country, but it's quite common in places where you have cold weather, is the heating and humidification process. Okay, so this is like a complementary process to the cooling and dehumidification process, which all our air conditioning system does. So if you have this as the initial state, this is cooling and dehumidification. The complementary process would be heating and humidification. So it's quite apparent from the name of the process that you have to provide steam to the incoming air. Okay, and the steam temperature would be higher than the incoming air temperature. So when air mixes with this steam, it will humidify definitely, and it will also pick up some sensible heat from the steam itself. So always try to understand what would be the two processes which will happen based on the incoming condition and the additional, if you have the additional stream of steam or air which is mixing. So based on these state points, you should be able to tell what is the process that will happen. So if you have a cooling coil, if you have a cooling coil whose temperature is lower than the dew point temperature, definitely you will have cooling and dehumidification. If you have just an electrical heater, you will only have sensible heating. If you, instead of supplying heat only through an electrical heater, you supply heat in form of steam, then definitely incoming air will heat up when it mixes with the steam, as well as it will humidify. So this is a very common process, psychrometric process, which is done in winter air conditioning systems. So whatever we use in our home in India is mainly classified as summer air conditioning system. So this is how a commercial humidifier looks like. If you open the boiler segment, you have these heating elements. These are the heating elements. This is your liquid water which is present over there. Okay, the steam actually comes out from this top side, And in case you want to drain the water, we have this valve to drain out the water. We also have a small pump to blow this water at a pressurized condition in order to blow out any scales which might get deposited. Okay, this may also be automated by using a timing loop. So after maybe several hours of operation, this pump will turn on. It will blow down the water, pressurized water, through this pipe in order to remove any scales which is present. Okay, and then you also have a filling cup. So there would be an opening here through which you can fill water. So all these processes or devices which we are looking at, they just form in on an individual level, they are just one of the air conditioning process. When it comes to a large commercial air conditioning system, you can have multiple such devices attached, catering to different zones. If you require in a particular area, you require cold and dry air, the air conditioner should be able to provide cold and dry air to that particular zone. In certain place, if you require cold but humidified air, again your AC should be capable enough to maintain that temperature and humidity ratio. Okay, so many such devices could be used in series uh, in order to attain your desired condition. This is again one example of a steam humidifier. So that humidifier generates saturated steam at 100 degrees C, and it is sprayed into the moist air. The moist air enters the humidifier at 30 degrees C, 30% relative humidity, with a mass flow rate of 3 kg per second. Steam is added so that the humidity ratio of the air increases by 0.01 kg of water per kg of dry air. So it gives you the delta omega or delta W. So incoming air state is given 30 degrees C and 30% RH. We are spraying some saturated steam into this incoming air. The air flow rate is given to be 3 kg per second. So air comes in at 3 kg per second. It mixes with steam which is coming at 100 degrees C, saturated steam, and it leaves as moist air. The amount of dry air flow rate would still remain as 3 kg per second, but omega is given. So omega 1 can be found from the given condition, 30% and 30 degree dry bulb temperature. So omega 1 is known. Omega 2 is indirectly given. So this humidifier is providing 0.01 kg of water per kg of dry air. So whatever this omega 1 is, plus this value will be your omega 2. From the given data, find the exit temperature of moist air. Okay. And what is the energy consumption of the humidifier if steam is produced by boiling liquid water which enters the humidifier at 30 degrees. So let's first try to answer the first part. Find the exit temperature of moist air. So how do we do that? How do we do that? So apply your energy balance. So m dot air at state 1 H1 plus m dot steam into H of steam, saturated steam enthalpy is given, equals to m dot air H2. Why I am just writing dry air is because I will be getting the enthalpy value from the psychrometry chart, and the psychrometry chart gives me all the enthalpy values in terms of per kg of dry air. So this is 3, this is 3. Enthalpy I have to get it from the psychrometry chart. This I will obtain by solving this equation. So this is known. This is also known. How to obtain the amount of steam? How to obtain the amount of steam? Apply the mass balance for the moisture part. M dot air 1 times omega 1 plus m dot v equals to m dot air. Anyway, 1 and 2 are same, so I can still write 1 to omega 2. So omega 2 is 0.01 higher than omega 1. So this is known, this is known. You obtain omega 2. Oh, sorry, m dot v. Okay, substitute over here. You will get the enthalpy H2. So once you get H2 and you know omega 2, so using these two properties, you can pinpoint the state at the exit of the of this mixing process. Remember, you always require two properties to determine the state. So once you determine the enthalpy at the exit, enthalpy at the exit is H2. You know omega 2, your state is defined. Omega 2 or W2. Okay, this is your state 1. This is your state 2. Once the state 2 is determined, you can read the temperature. So part number B is we have to find out the energy consumption of this humidifier. So what you have to do is your rate of steam production is m dot v into HFG plus Cp delta T, because the temperature of water that you will supply into your humidifier is 30 degrees C. So it has to be brought to 100 degrees C and then the latent heat of vaporization. Okay, so whatever the latent heat of vaporization is plus the Cp delta T, Cpw, water. So you already know the enthalpy of saturated steam. From this question, you also know the enthalpy of liquid water. You can also just subtract these two values. This will be equals to this value. You see in the answer, there is only very small amount of sensible heating and very large amount of moisture rise. So 10 grams per kg of dry air, which is quite significant actually. So your process line, if this is state 1, the state 2 temperature is almost 30 only, so only 1 degree rise. So it's the process is like this. When you use a steam humidifier and mix this steam into the incoming air, the process that you follow is definitely heating plus humidification, but the sensible component is quite small. So you're almost moving on a vertical line. It's not exactly vertical, but almost vertical. So in case you want further heating, so you will have to put a preheating coil. So after this, you can provide a heating coil, and this could be your exit state. So your winter air conditioning systems will include a steam humidifier first and then a heating coil. So whatever temperature you get from the steam humidifier, if that is not sufficient to heat the room, you further raise the temperature by using a heating coil.
Sir,
Yes.
so for the previous question, the last part,
Yes.
the liquid water is enters in 30 degrees Celsius. Means at first we have to multiply mv dot into Cp delta T. Means the enthalpy difference between 100 and 30.
Yes.
And sir, do we also need to add the latent heat at 100 degree?
Yes. So finally, what you get is a steam, saturated steam state. Na? So this is what you should do. But the question already provides you the answer in a very simple manner. It gives you the enthalpy of the saturated steam and it gives you the enthalpy of the liquid water at 30 degrees. So directly take the difference.
Okay.
Suppose I had given you the data in a different manner, I could have given you that 2400 kilojoules per kg is the latent heat of vaporization at 100 degrees C. And then with this information, and this is the enthalpy of liquid water. So now with this information, then you will have to do HFG plus Cp delta. This is the last process, the psychrometric process, which we'll discuss as part of the air conditioning processes. So this is dehumidification using desiccants. Desiccant material is any material which has affinity to water vapor. Silica gel, zeolite. So these are materials which have affinity to water vapor. Any salt, in fact, even your common salt NaCl has affinity to water vapor. If you keep your NaCl open in humid environment, you will see that water, it becomes a slurry kind of material after some time. So it absorbs water. Now, whenever you have absorption, you have phase change. So water is present in air as water vapor. But when you have any salt solution which is kept, or it could be solution, it could be dry salt also. Okay, it could be so silica gel, zeolites. So these are all dry powders or dry granules. You can have NaCl dry, or in fact you can also have NaCl solution also. Even that solution, if you keep and if you can measure the liquid height, after some time you will see that the liquid height has increased. Okay, there are other salts like LiCl, lithium chloride, lithium bromide. So these are all salts which have affinity to water vapor, even in the solution form also. Okay, so the state of water after absorption is actually liquid water, and that's why they form a jelly-like substance after they become saturated with water. So air has water in form of water vapor, but when they get absorbed into these salts or into these materials, silica gel, zeolite, it changes its phase and it becomes liquid. and hence it occupies less volume. And that's why even a small amount of silica gel or zeolite is good enough to absorb large amount of water vapor. Okay, so the people will say that silica gel granules have lot of pores into which what this water vapor enters and gets absorbed. Okay, but the absorbed phase is actually is like liquid, and that's why it occupies less volume, and even in the small pores the mass of water that gets absorbed is quite high. Normally 1 kg of silica gel can absorb as much as 400 grams of water vapor. Okay, whereas 1 kg of dry air typically will have 10 grams of water vapor. Okay, because water present in air is in vapor phase, whereas water which enters and gets absorbed, so there is a phase change process which is going on, and hence you can measure the temperature of silica gel, you will see that the silica gel temperature goes high when this process happens. So these materials are called desiccant materials. So any material which has affinity to water vapor is called a desiccant material. So what we do is we create a wheel. Desiccant. This is a wheel. Now this wheel has this porous mesh, and within this mesh we place the silica gel particles. It could be in form of powder or it could be in form of granular structure also. Okay. So this entire porous region would be filled with silica gel, and your process air which you want to dehumidify will pass through this, come in contact with silica gel and leave as dry air. Now why we create a wheel is it will be apparent now. So once the silica gel gets saturated with water vapor, it cannot absorb further. So we have to regenerate that silica gel or zeolite or whatever salt you use. So we make this wheel, and as you just imagine that you have a duct like this. So on this side of the duct, the air is getting dehumidified, and there is a motor which is rotating this wheel. So this part of silica gel gets saturated because it is absorbing all the moisture. Now as you rotate this wheel, this portion will come down here. After some time this portion will also come down here. Now there is another duct at the bottom side. We supply hot air to this bottom side, and then this hot air, so it could be of the order of 70-80 degrees C also, this high temperature air will then regenerate the silica gel. By regeneration I mean it will desorb. So you have absorption happening here, it will now desorb the silica gel. So water vapor will, so water in the pores will now come out as water vapor. It will now mix with the incoming hot air and go as wet air. So you have to provide hot and dry air over here. So it is normally difficult to dry. So anyway, we were drying our air using the silica gel. So where will we get this hot and dry air? So what we do is we just provide hot air. So when you raise the temperature of air, if you remember, PV over P sat at the rate temperature of the air. So if you raise the temperature of the air itself, then you have scope of having higher moisture content in this incoming air. So if you raise the temperature of air from 40 to 80, okay, 40 degree corresponding to that, you can have a partial pressure of water vapor of around 8 or 9 kPa. Corresponding to 80 degree, you can go up to 50 kP. So you have more scope of now releasing moisture into this incoming air. So that's why we heat this air and then allow it to pass through the silica gel. Now the incoming hot air has potential to take up moisture from the silica gel. So it picks up moisture and it makes it drier. And now this dry silica gel goes back to this side, and again this process here passes through that and it gets absorbed. So top part you have absorption, bottom part you have desorption. Silica gel becomes uh, uh, a jelly-like substance on the top surface, and it becomes again dry powder on the bottom part. Now from where do we provide this heat? You can either provide it through electrical heaters, but then it will defeat the purpose of using this dehumidification uh, uh, process by using this desiccant material. So most of the time people use solar heaters or some industrial waste heat which is available. You can use electrical heaters, but then again it will then reduce the efficiency of the overall process. Now where do we use this desiccant material is wherever you require very dry air. Can you name one place where you require very dry air? Any application? Think of semiconductor fabrication labs. If you have large amount of humidity, what will happen to your chips, which is getting fabricated over there? So wherever you require very dry air, we go with the desiccant dehumidification process. Okay, and wherever you have desiccant material, you absorb in one part of the process and you have to desolve in another part. And that heat has to come either through electrical heaters or through solar heaters, or in case you have some kind of an industrial waste heat. Let's say your semiconductor fabrication lab is next to a power plant where there is some waste heat. Then you can use that waste heat to regenerate this desiccant wheel. If that is not available, you can do it in a renewable manner by using solar heaters. If both of them are not possible, then you have to resort to electrical heaters. Okay, so there are a lot of salts which we can use, LiCl, LiVr. Okay. NaCl is also up to a certain level, but it cannot come close to these salts. But you can practically see in your home if you are in Kolkata, any place where humidity is quite high, especially now, you can see if you just keep your salt outside for a long time, it becomes a jelly-like substance. What is the process line if I just look at the humidification part? If this is your inlet condition, we will not look into the regeneration part. We'll assume that silica gel has enough uh, pores available for air to be continuously dry. So this is your state 1, air comes in at this state. After it passes through the silica gel, it goes to state 2. Assume that this entire box or this duct is insulated. What would be the process line? It will be isenthalpic process. So H1 will be equals to H2. There is no heat transfer from outside. I am not supplying any liquid water, any steam to this box. So ultimately what you have is an isenthalpic process, and you will see if you follow this isenthalpic line, as you decrease your moisture content, the temperature keeps on rising. Okay, and the reason is, if you are able to decrease your humidity content in your air, it means that water vapor has changed its phase into water. That's the only way you can extract water from air. You have to change the phase of water vapor to liquid water, and that's why the exiting air has less moisture content. Now, where does this latent heat of condensation go? It has to go to the incoming air only in the steady state condition. Definitely, it will also warm up the desiccant wheel, it will warm up all the ducts. Okay. So, this phase change process from water vapor to liquid water is what is raising the temperature of the incoming air. So what you get at the exit is hot but dehumidified air. Okay, but if you look into the physics of the process, the correct form of this phase change is water vapor getting absorbed into your silica gel, and this absorption process actually releases heat because it is equivalent to phase change process. But if you don't want to go into all those details, so you can simply understand that water vapor in air has changed its phase and gone into the silica gel. So whenever it changes its phase, it has to release some heat. Where does that heat go? Into this incoming air stream only. So solving part is again very simple. You just follow an isenthalpic process line. Incoming air state is given 30 degree and the moisture content is given as 10 grams of water in 1 kg of air. So W2 is given, W1 is given, sorry. And it is dehumidified so that the exit humidity ratio is only this much. It's 0.2 gram. Oh, sorry. So 10 grams and it is 2 grams. It has reduced by 8 grams. So 10 grams to 2 grams. So find the temperature of the air at the exit. So you have to follow the isenthalpic line. Isenthalpic line is that black slanted lines on your psychrometry chart, and wherever you have this 2 grams per kg of dry air, that is the exit state, and read the temperature. You can see the temperature is around 50 degrees, so from 30 to 50. Okay, but check the exit relative humidity. It is only 2.6%. Extremely dry air can be obtained by using this desiccant material. Okay. Now you can compare it with our cooling and dehumidification process. If you have this as your initial state, if you pass it through the desiccant material, you can attain any process line on the isenthalpic line. So any state on this isenthalpic process line. Okay. Whereas if you go by the cooling and humidification coil method, this is the limiting W2 that you can get. This is your initial, this is the final. You cannot go below this W2 with a single cooling coil. You will have to cool, then heat, and then again cool, and then heat. So you will require so many components. Whereas with your desiccant wheel, you just follow the isenthalpic process line. Wherever you want, you can have the exit state. But the penalty over there is you are continuously heating the air also. So later on, if you want to attain the same temperature as the inlet temperature, you can pass it through a cooling coil and just sensibly cool. Okay, so there are various ways of obtaining the same processing. So this this was the method which we have discussed. Suppose you want to just dehumidify from here to here, you can cool, heat, cool, heat. That is one way. Or you can pass it through a desiccant material and then cool. And which process to follow will be dictated by, of course, the application. So how dry is the temperature, is the air that you require at the exit, and what is the temperature of the air required. If you are fine with 40-degree air, or if you are fine with 35 to 40-degree air, then 50-degree cooling it to 40-degree is not that much of a penalty. But suppose you require 20-degree or 15-degree, then maybe you will have to compare the dehumidification process followed by a sensible cooling process, check how much energy you have to supply, and check if you were to use a cooling and dehumidification coil for the same process with maybe multiple reheating process and then multiple cooling and dehumidification. So check which is better in terms of energy consumption. Any doubts? Okay. So many a times in air conditioning processes, you can have multiple streams. Just like in your thermodynamic processes, you would have discussed about mixing of two streams of air or two streams of any liquid or any fluid and forming one single stream. Similarly, over here also you can have two different streams of moist air coming and mixing and forming one single stream of moist air. So the mass and energy balance equations, they remain same. So if you were to write the mass balance, it would be Ma1 plus Ma2 equals to Ma3. This is for air. To write the same equation for water or moisture content. Okay, and the energy balance equation is the enthalpy balance. Okay, we can also, if you have two streams, then we can easily plot it on our psychrometry chart also. So if you have one stream having this as the state, another stream having this as the state, you join these two streams and your final state will lie somewhere in between these two state points on this line. Now if you have large mass flow rate, let's give some numbers. If you have large mass flow rate at state 2, then your final condition will be closer to state 2. If you have larger mass flow rate of air at state 1, you will have final condition here. If you have equal mass flow rate, it will be in between. So if you have two streams, you can directly join these two lines and find out the exit state based on the mass ratios or ratio of mass flow rates of the two streams. If it is 1:1, then it will be midpoint. If it is 100:1, so then whichever has 100 times more mass flow rate, the exit state would be closer to that. You can also have mixing, which can lead to condensation. So let's say your one state is this, the other state is this, and if you join these two, okay, let's say you have 1:1 mass flow rate. So 1 kg per second of state 1 air mixes with 1 kg per second of state 2 air. So your exiting state is this. And if you draw it on the psychrometry chart, it can go beyond your saturation line. So what does that mean is, you simply check the temperature. Okay, draw a vertical line. So your exiting state cannot be having relative humidity more than 100%. So your exit state would be this, with this much amount of water condensing into your box itself, in your mixing box. So if you have 1 and 2 mixing and your state 3 is such that the relative humidity is higher than 100%, then it simply means that you will have water getting collected in this mixing chamber and the exiting state would be 100% at that particular temperature. Any doubts in the mixing part? Okay. So this is quite common. If you actually look at this mixing process, this is quite common in our home. If you have extremely cold room, you have made it cold by using your AC, and you suddenly open the door or window, okay, where the outside air could be hot and humid, then you can actually see water vapor condensing on your window grills, on your arms, on the floor. Okay, because everything was cold inside. So this state point 2 got mixed with state point 1 and it created an intermediate state which led to RH greater than 100%, which means that you will have condensation. Any doubts in any of the processes, any of the devices we have discussed? Okay. So now let's come finally to the summer air conditioning system. We will discuss two systems, one without any active ventilation, which is what happens in your split ACs, and the other one is with an active ventilation, that is the system provides you fresh air from the outside. Okay, that system is used in your central ACs. Your central ACs have provision of bringing in outdoor air, mixing it with the indoor air, and then or the cold air, and then providing it to you, so that you don't feel lethargic or what we call as the sickness that you feel when you are always in an air conditioned environment. That sickness comes because of lack of oxygen. You continue to recirculate the indoor air without bringing in fresh air, you feel sick or you feel tired, no energy. That is because of no ventilation or poor ventilation. And this is what happens in your split ACs. So your split ACs do not provide you ventilation, but that doesn't mean that the CO2 composition continues to rise in your room and your O2 level goes down. That does not happen. Can you tell me why? If you have absolutely no ventilation, in fact, you cannot survive in that room. But you don't feel that in your bedroom. You are able to sleep in your bedroom, but your AC is not providing you any ventilation. It is just recirculating the air. From where is the ventilation happening? There must be some place through which you are getting fresh oxygen. Otherwise, you cannot survive. What is that place? Or how you are getting that fresh air from outside? Anybody? It is basically through the gaps in your windows and door frame. If you just close each and every vent, each and every gap in your door frame, in your windows, make it completely airtight and run your AC. You will feel thermally comfortable, but you will not feel uh, energetic after some time. You will feel suffocated, and you can in fact feel that the air that you are breathing in has some weird smell, because the all the air which you are exhaling is just getting recirculated back to your room by the indoor unit of your split AC. It's not a very healthy situation. So your AC mechanic or everybody will advise you to close all the scope for ventilation, close all the gaps you have in your window frames or your door frames when you are installing an AC. But then you must remember that if you close each and every gap, where will you get the fresh air from? Your car ACs have the provision. Okay, there is a knob. If you turn on that knob, you will get fresh outdoor air. Because in your car, it is even more tighter. You have very little scope for air leak once you pull up your windows. So your car ACs have a setting, a knob, which provides you fresh air from outside. Your split ACs do not have that. Some of the window ACs have that provision of getting fresh air from outside. So if you look at the psychrometric processes, what is happening is a very simple process. Uh, so this is your room. This is where you will install your indoor unit. For the time being, we are just focusing on the air process. So the air conditioning apparatus is shown as if it is outside the room. Okay, but it is still inside the room only. It is just that the air is getting sucked in to the from the top side of the indoor unit, and it gets recirculated back from the bottom side. So instead of showing it in that manner, this schematic shows as if the apparatus is outside the room. Air is getting drawn into the apparatus here, and it exits and is blown back into the room. But this entire process is happening inside your own room. Okay, and this apparatus is nothing but the evaporator. So this cold and dehumidified air is supplied, and it picks up sensible heat and moisture, and then again gets circulated back into this cooling coil. This is the process which is happening. Now what is this QS and QL? So QS is that part of the heat transfer which corresponds to sensible, and L is the latent, that is the increase in moisture content. Now what is the source of sensible heat? Definitely the heat leak from ambient to the indoor through the walls and the roof. Okay, combination of conduction, radiation and convection. So during the daytime, solar radiation is the major component of the heat gain. That is sensible. That goes into the sensible column. Okay, you can have some gaps in your doors and windows, so air infiltration into the room. That will also bring in some sensible as well as some latent, because it will also bring in some moisture from outside. So if you have air infiltration into the room, it will go partly into the sensible heat as well as into the latent heat. But if you look at just the heating that you get through the walls of your room, that goes into the sensible column. So your radiation, through radiation the walls get heated up, and then it starts to conduct, and then through convection inside the room you will have the heat getting inside. Okay, then you, human, sitting inside doing any activity, will also be releasing heat, both in form of sensible as well as latent. So you will perspire, that perspiration will increase the moisture content inside. So in order to accurately size the system and what should be the operating condition, one must know what is the total load on your system. Okay, so system being your air conditioning apparatus, that is the evaporator, and what fraction of it is QS and what is QL. Because remember, the psychrometry process line gets fixed only when you know both the total enthalpy change as well as the fraction of it going into sensible and latent. That only determines the slope. Okay. Now what temperature to maintain inside the room is up to you. So that is your thermal comfort. So let's say the temperature inside the room has to be maintained at some I denoting the indoor air temperature, and let's say the humidity ratio that you are comfortable at is Wi or omega I. Okay, so this is the steady state condition inside your room you want to maintain, and your room has QS amount of sensible heating and QL amount of latent heat transfer. Now this air goes into your air conditioning apparatus, cools down to a condition denoted by Ts and omega S or Ws, comes back into the room and gets mixed, and then again leaves at T indoor and W indoor. So this is the process that the air follows, as simple as that. Supply air going to your indoor room condition, then it goes in back into the coil and comes back to supply air condition. So this is the process. So this straight line going up and going down. Again, this is only at steady state. At unsteady state, these two lines will not match exactly. Now when the supply air, which is the air leaving your indoor unit at this state, comes into the room, it will pick up the sensible heat, it will pick up the latent heat and come to this temperature and humidity ratio given by I. It will then go back into the indoor room unit, gets cooled and dehumidified, reaches this state S, and then comes out of this coil. So your air conditioning system has to balance out this QS and QL. If there is a mismatch, then definitely there is no steady state at all. And you will continuously fiddle around with the temperature. If you are not able to balance the sensible or the latent heat load, you will feel that you are not feeling comfortable. So you are the feedback, and the input to the AC is you pressing certain features in your remote. Either you will go to dry mode, or you'll increase the fan speed, or you'll reduce the coil temperature. So all these things you will do, so that the final I inside your room is your own personal thermal comfort. So as far as the analysis part goes, it's quite simple. So if you want to maintain a steady condition I inside your room, and if you know what is the sensible heat transfer and the latent heat transfer, and then you can actually determine the the state S required, and if you join this line I to S and extend it to R equals to 100%, you will get the apparatus dew point. So this gives you an idea of the coil temperature that needs to be maintained in your evaporator or your what you call as indoor unit. Okay, then you can also obtain the bypass factor. All the heat exchanger characteristics that we have discussed can be obtained. But for that, you need to know what is the temperature you want to maintain inside the room, what is the humidity ratio you are comfortable at, and what is the fraction or what is the total load and what fraction of it is latent and sensible. So all this information needs to be there if you want to appropriately size your system and exactly maintain the desired condition. So there are some terminologies which are given. So there is something called RSHF. So SHF is sensible heat factor. R means the room. In this case, in order to attain the steady state, your RSHF has to be equal to your CSHF, that is coil sensible heat factor. So the amount of dehumidification and cooling that you do in your evaporator coil has to match the load in your room. So here comes the next difficult question is, what is the thermal comfort zone that we must design our ACs for? Now this is a very difficult question to answer because it all depends on the personal choice. By personal choice I mean where were you born, what was your culture. So what kind of food you eat can also determine what is your thermal comfort. That is the level of research that Ashray has done in obtaining data for thermal comfort zone. Kind of food, the kind of clothing, where you have lived all throughout your life. Okay, that everything boils down to your own personal history and culture, and that defines your thermal comfort zone. A person who has always lived in the mountains and suddenly comes to a central region of India, okay, he or she will feel it to be very, very hot. Need not be humid. Whereas a person living in Chennai goes to Delhi, he will find that Delhi is slightly hot, but very, very dry in summer. Okay, and the clothing also determines. People from European region, when they come and visit our country and they wear all the suit and full trousers during summer, they will feel that it's very uncomfortable even in an air conditioned environment. So the thermal comfort is a very personal thing, and all Ashray can do is conduct a huge amount of survey and create some kind of a guideline where majority of the people feel comfortable. So this shaded region is where 80% of the people for whom Ashray had done the survey, again Ashray being an American organization, they have conducted the survey in America, which I feel is a good representation because the American country has a large span in terms of latitude. Okay, and it also has a large mix of various people. Doing the similar survey in India may not lead to a more comprehensive result than doing the survey in, let's say, in America or Canada, where a lot of immigrants are also there. So this is some kind of a ballpark region where you can operate your air conditioning system. So definitely your AC will operate at one particular set point only. So if at all it is within this region, most of the people will feel comfortable. If you go beyond this, you will feel hotter. If you go this side, it is cooler. If you go down, it is drier. If you go up, it is humid. If you guys were conducting the experiments physically, then even we also create some sort of a database and we provide it to you at the end of the lab class that see this is the survey we have conducted throughout the lab class. So this is the sheet and this is the outcome of that survey. And then you can locate where you feel to be thermally comfortable and where others feel that they are comfortable. So this is the ASTRAI recommended form or sheet to collect the survey. So you see that for your given environment, you have to specify, are you feeling cold, cool, slightly cool, neutral. So these are the scales which ASTRAI has recommended. Okay, what kind of information they collect other than the thermal comfort is what kind of dress you are wearing. They also collect the information that do you feel that if you increase the air movement, you would feel more comfortable. So air velocity is also an important factor. Okay, so this is the survey form as recommended by ASHRAI, and based on this, they have collected huge amount of data and created that zone of thermal comfort region. So one cannot pinpoint and tell that one particular condition is the perfect condition that your AC should maintain. One aspect which is not mentioned over here, which ASHRAI also collected, is your background also, ethnicity, where you were born, where you have stayed. So these information also they collect.